Welcome back to MLT 120. Today we're going to learn how to use a hemocytometer. If you'll look down at the bottom of the page, this is what a hemocytometer or one design of a hemocytometer. And we'll be using the hemocytometer on the microscope to count cells. So the purpose of doing a hemocytometer lab is to count cells in the laboratory manually. Most cell counts are now performed using automation or automated analyzers. However, sometimes it is necessary to still perform manual cell counts. Often cell counts are performed on body fluids, but it is possible to still do cell counts on peripheral blood. And examples of body fluids that could have cell counts done on them is spinal fluid, pleural fluids, abdominal fluids, things like that. A hemocytometer is a specialized slide with a counting chamber used to perform manual cell counts. We can count any kind of cell, whether it's a red cell, white cell, sperm cell, whatever type of cell we're looking for and need a count on. We could use a hemocytometer to count the number of cells. And you can find an image of a hemocytometer on page 156 in your textbook. And again, we're counting inside a grid pattern that is on the slide. So this is a specialized slide that we use to perform the manual cell count. And just to note, the hemocytometer contains two grids because we're going to count one grid to start with, and then we're going to go over to the second grid and count the second grid, and we're going to take the two numbers from each individual grid, add them together to get an average cell count from the two grids. Okay, so this is to show you the grid pattern on your hemocytometer. So you have two of these grid patterns on your hemocytometer, and this will be roughly what each hemocytometer looks like. It may differ a little bit varying on the brand of hemocytometer you're using, but you have basically 9 large squares, 1, 2, 3, 4, 5, 6, 7, 8, 9. And each of these large squares are usually used for white blood cell counting. And that's what this W is here for, is representing white blood cells. These smaller squares are usually used for red blood cells. So this small little square right here is for red blood cell counting. And we usually use the outside corners of the center square and the very center small square for counting red blood cells. So anytime moving forward, when we're referring to a large square, we're referring to this size square. Anytime we're referring to a small square, we're referring to a little tiny square here in the center of the grid pattern. So now let's talk some specifics about our grid pattern for our hemocytometer. That whole grid pattern, the entire area, is 3 times 3 millimeters squared for all 9 squares. And again, it's divided up into 9 equal large squares, and each has an area of 1 millimeter squared. That's length times width, and the depth of the cover slip is 0.1. That's from the bottom of the cover slip to the top of the slide. That area there is 0.1. So our volume is length times width times height depth, and it's reported as millimeters cubed or microliters. The volume of the hemocytometer squares, we've already mentioned this, but some of the squares represent white blood cell counting squares, and some represent red blood cell counting squares. And the white blood cell counting squares, we usually use the outside corners, and we use the larger squares. And usually in pictures or diagrams, a W represents those larger white blood cell counting squares, and in diagrams a R represents the smaller red blood cell counting squares. Sometimes we use those smaller squares also to count platelets, and we determine the volume of each square by finding the length times the width times the depth. So let's talk about the volume of the larger white blood cell square. In the white blood cell square, it has the length of 1 millimeter and the width of 1 millimeter. The depth, of course, is the 0.1 millimeters. So if you figure that up, 1 times 1 times 0.1 is 0.1 millimeters cubed or microliters. So that's the volume of the white blood cell square. And you'll need to remember this number because this number is going to be important in our formula or our calculation that we're going to have to use in order to find our average white blood cell count a little bit later on. Now let's discuss the volume of our red blood cell counting square. So remember that our large square was for the white blood cell and our small little square is for the red blood cell counting purposes. So there are 25 smaller squares in the center square, and we divide that 0.1 by 25, and the result of the volume of the small square is 0.004 millimeters cubed or microliters. Okay, remember we got the volume of just one of those 9 squares is 0.1, and that's what we're dividing by 25 because there's 25 of the small squares within one of those large squares. So that gives us the volume of our red blood cell counting square, which is 0.04 millimeters cubed. And again, you'll need to remember this number because we're going to need it for our formula or calculation when we're finding our average red blood cell count in a few minutes. So remember that for white blood cells. Remember this number for red blood cells. Again, these both numbers are our volumes for those squares. So just for reference, let's look back at our grid pattern. So for this entire square here, for the volume for this entire white blood cell counting square is 0.1 millimeters cubed or microliters. Okay, each one of these large squares, each one of these 9 large squares are 0.1 millimeters cubed. The volume for this little tiny square, and there's 25 in each large square. So if you count all these, there should be 25 small squares within the large square. The volume of each one of these is 0.004 millimeters cubed or microliters. So that's what we were just talking about. The volume for each of the large squares and the volume for each of the small squares. Now let's actually go over the formula that you're going to use to find out your total cell count for a sample. So the formula is the number of cells counted, and this will be your average number of cells counted, times the dilution, if a dilution was used, times the number of squares counted, and this is the number of squares on your grid pattern for your hemocytometer, times the volume. And this is why we need to know the volume, the numbers that we just went over, whether it's a large square for the white blood cells or a small square for the red blood cells. This is where that's going to go in, those numbers. So you want to make sure that you know this formula because this is the formula that you're going to need in order to come up with your total cell count. So why do you think we would need to do a dilution in a specimen when we're performing a cell count? We often need to do a dilution because the cells may be so numerous in number and clumped so closely together that we can't count them accurately unless we dilute them down until we can see the individual cells. So by diluting, they're easier to count. However, if we do a dilution on a sample, we must put that dilution factor into our hemocytometer formula in order to calculate the correct cell count. Okay, when we're counting our cells, we've got to determine which cells to count, whether we count the cells that are laying on the grid line or if we don't count cells that are laying on the grid line. And the reason that we do not count all the cells laying on the grid line is because if we end up counting all the cells on all the grid lines, we're going to end up skewing our cell count to the high side. Okay, and then on the opposite side, if we decide not to count any cells that are halfway online, then we're going to skew our number low for our cell count. So the way that we solve that is we pick two sides of the square and we count the cells on those two sides. Okay. And I'm going to show you an image in just a second that kind of shows you how to do this. It doesn't really matter which two sides you pick to count cells on, but you just pick two sides. You don't want to pick all four because that's going to skew your cell count high, but then you don't want to not count any of the cells on the grid lines because that's going to skew your number low for your cell count. Okay, so this is an example of one of the large squares. Let's say this is a white blood cell square that we're counting. And imagine these are all cells that are laying on the outside grid line of the cell. So again, we do not want to count all these because that's going to skew our number high. Okay, this would, if you counted all of them, you would be counting cells that are laying on lines on all four sides. That would skew our number too high. But we don't want to not count them because that's going to skew our number too low. So what we have done here is all the ones that are green, the grid line that's on the left-hand side and the grid line that are on the top, we are counting these cells in our cell count number. Okay, we've picked two sides and we're including these cells in our number or in our count. The cells that are in red on these two sides, the bottom and the far right, we are not including them in our count. So we're getting the closest average we can for our cell count without skewing too high or skewing too low. Now let's talk about a manual white blood cell count. If we have an order for a white blood cell count and we are not worried about a red blood cell count, we can dilute it down using a solution that actually lyses our red blood cells and gets them out of the way visually. So we're just leaving our white blood cells available to count. And we can use a 3% acetic acid as a diluent and a lyse agent to lyse those red blood cells and get them visually out of the way. So we are just looking mainly at our white blood cells to make them a little bit easier to count because we're not trying to look through all those red blood cells to find our white blood cells. For our manual white blood cell counts, we typically use a dilution of 1:20. That's not to say that you couldn't use a different dilution. That's just typically what's used. We usually allow 10 minutes for our red blood cells to lyse in that solution of 3% acetic acid. And once we have that incubation period of 10 minutes over, we can load our specimen onto our hemocytometer on both sides of the grid lines on the hemocytometer. Then you can put the hemocytometer slide on the microscope and begin to read. For the white blood cell count, we're typically going to count the 4 large outside corner squares, which are typically our white blood cell counting squares. You're going to record the results. And remember, you're counting both grid squares. You're going to add the two counts together from each grid square and average. You can average the results and see if they're within 10%. If there's a difference greater than 10%, you're going to have to repeat your counts for your white blood cells. So this slide is just showing you how to calculate the difference to see if it's within 10% for your hemocytometer. So you're going to start and you're going to identify your count for side A versus side B. Remember, you have two squares or grid patterns on your hemocytometer. So one is A and one is B. You're going to find the difference. So let's say you counted on one grid square, there was 23 cells counted. On the second grid square, there was 20 counted. So the difference between 23 and 20 is 3. You're going to find their average. So you're going to do 23 plus 20 and divide by 2. So you have an average of 21.1. Then you're going to take the difference divided by the average, multiply it by 100, and that's going to give you your percentage. And the percentage on this example is 13.95, which is greater than 10%. So if you ended up with this count, these two counts for your hemocytometer counts for each side, you would have to repeat your count because it's not within 10%. A difference greater than 10% between the two numbers, the count has to be repeated. So now that we've learned how to use the hemocytometer, let's look at an example of a calculation. So a tech performs a manual white blood cell count using the 3% acetic acid for the diluent, and it makes a 1:20 dilution. So on the first grid side of the hemocytometer, she counts a white blood cell count, and she counts the 4 corner white blood cell squares, and she counts 52 white blood cells. On the second grid, she counts the same number of squares. Again, she's counting the 4 large corner squares, and her result is 58. Their results are within 10%, so she averages the two counts at 55 white blood cells. So let's plug everything from the example we just looked at on the previous slide into the formula so we can get an exact white blood cell count for this patient. So we have an average of 55 white blood cells counted. Okay. Then we have a dilution factor of 20 because she used a 1:20 dilution. So we only need to use the 20, the dilution factor. She counted 4 squares on each side. And then we need to know the volume of the large white blood cell counting square, which is 0.1. Okay. When you do the math, 55 times 20 is 1,100. 4 times 0.1 is 0.4. So the total white blood cell count for this patient is 2,750 per microliters or millimeters cubed. Now we have to ask ourselves, is that in normal range for a white blood cell count for a patient? Well, our normal range is between 4,500 and 11,000 white bloods per microliter. That's our normal range. So if we look back at this number, if we get a white blood cell count for a patient and it's 2,750, guess what? That means their white blood cell count is low. So we just talked about white blood cell counts, but let's talk about red blood cell counts on our hemocytometers. When we're performing manual red blood cell counts, we typically do not do those on peripheral blood just because there's so many red blood cells to count. Usually we do that on an automated analyzer, but however we do perform red blood cell counts on body fluid specimens a lot of times manually. If we do end up needing to make a dilution on a body fluid specimen, we must make sure that we use a saline that is an isotonic solution so our red blood cells do not lyse. Also, we don't want crenated red blood cells. We want our red blood cells nice and happy so that they're easy to count. If our red blood cells lyse, we're not going to get an accurate count, and we're not going to have accurate results for our patients for a red blood cell count. So let's look at a practice problem with red blood cells or a red blood cell count. So a tech receives a bloody peritoneal fluid specimen in the lab with a red blood cell count request. Peritoneal is another way of saying fluid from the abdomen. He makes a dilution of a 1 to 100 using saline. So he loads both grids on the hemocytometer, and he counts 5 of the small red blood cell squares on both grids. Okay, so we're dealing with the small red blood cell squares in the center instead of the large white blood cell squares. On the first grid, he counts 125 red blood cells on 5 of the red blood cell counting squares. On the second grid, he counts 132 red blood cells on 5 red blood cell counting squares. His results are within 10%, so the average is 128.5 red blood cells. So now on the next slide, let's plug that into the calculation. So we're going to plug in the average for both sides of 128.5 red blood cells times our dilution factor, which is 100. And then next we're going to put 5 down for the number of squares counted on each side. He counted 5 of the small red blood cell counting squares. And now we've got to refer back to the volume of that small red blood cells counting square, which was 0.004. Okay, and then if you do the math, 28.5 times 100 is 12,850, and 5 times 0.004 is 0.02. And then you divide 12,850 by 0.02, and you should get 642,500 red blood cells per microliter as your answer. And just to note, for normal range, there is no normal values for red blood cells in body fluids such as our peritoneal or our abdominal fluid. So we report the result that we get to the physician, and it's just 642,000 red blood cells, and it's a lot of red blood cells to be in peritoneal or abdominal fluid. Okay, just some facts to know. Make sure you remember your volumes for your white blood cell counting squares versus your red blood cell counting square volumes. Our white blood cell is the 0.1 millimeters cubed or microliters, and the red blood cell counting square volume is 0.004 millimeters cubed or microliters. Also know the general hemocytometer calculation. Make sure you memorize that. For the counts, if they don't agree within 10% of each grid between each side A and side B, you must reload the hemocytometer and repeat the count. Because most counts of peripheral smears are done on automated analyzers, most hemocytometer counts that you're going to perform are going to be on body fluids, but we can also use the hemocytometer to count things like sperm counts for fertility studies. And this image here is actually showing you sperm cells on a hemocytometer grid pattern. So for the Unit 2 exam, be able to calculate a manual white blood cell count and a manual red blood cell count given information like the examples that we went through today in lecture. Also, you will be doing a little bit more with the hemocytometer when you get to MLT 111, urinalysis and body fluids. This concludes our hemocytometry lecture. We'll be doing some activities in class dealing with the hemocytometer, and we'll be looking at a hemocytometer in class, and I will see you over in the next lecture.